forgot to take the cover off the camera there. So, hello everybody. Welcome to 302 Online, video 3. Technically the fourth time we meet, but video 3. So, hope you all are doing good today. Hello. So, today we are going to continue off of what we were talking about last time, which was asymptotic complexity. And hopefully today we will get into recurrence relations. So let's go ahead and recap a little bit of what we did last time and kind of complete that sort of idea, since it was pretty interesting stuff and also pretty important. So let's just kind of go from the top. So we started the day by talking about the two big things that matter when we're creating algorithms and data structures, and that is space and time. And space tends to be related to how we are storing the data in the computer to be able to process the data or simply to store it. And so there's RAM and hard drive and secondary storage, which would be hard drive or solid state drives. In the side of time, of course, time is just time in terms of seconds, but you know, it's kind of hard to compare to computers because they have different speeds and things like that, so it's not easy to just measure things with a timer and whatnot. So another way to look at things in terms of clock cycles, or better yet, just operations per second. And so from there we started to kind of do a little bit of algorithm analysis and figure out that a good way to represent how fast or how much space a program takes is in terms of its asymptotic complexity, which is measured in three main things, of which we talked about. We talked about big O, we talked about big omega, and we have yet to talk about big theta. I don't know what all those little like multiple with the little v things means, but yes. What is big O? So big O is going to be your upper bound relationship. Typically, the way to kind of think about it for now is to think of it as the worst case scenario of our algorithm. So if we have this really cool algorithm that can transform from A to B, our data, what is the slowest time that it's going to take? And let's really think about why it would make a difference. And why is it not always the same time? Well, again, we go back to sorting because it's what we know. When you're sorting something, it really depends on the state of your data. Some algorithms, the more sorted the data is, the faster they finish. If I was to tell you, if I gave you a deck of cards and I said, here's a deck of cards, you're going to look at that deck of cards and you're going to perform your own sorting algorithm. That's going to be kind of probably like a mixture between insertion and selection sort. You're not going to be doing bubble sort. We don't do that natively. We'll talk about that when we talk about sorting. But you, if I give you a deck of cards, you're going to look at them probably. And if they're almost sorted, then you're not going to unsort the thing. You're just kind of going to finish it off, right? So that's going to take you less time than if you got something that was just completely unsorted. Now, let's say I give you something in the sorted manner, but in like descending order, and I'm asking you to sort it in descending order. Well, you're looking at it, you pretty much notice immediately away that it's sorted just backwards, and then you just basically flip it and you're done, right? So depending on the initial order of the data is going to affect how long it's going to take for you to sort it, right? You can kind of see that. With some algorithms, it doesn't matter. They take the same amount of time regardless of the input. But a lot of the algorithms will vary depending on the input. So what we want to really look at is what is the worst case scenario in terms of the data. Sometimes we'll talk about that with different sorting algorithms, for example. Like, what is the worst thing that you can feed? As an example, by the way, bubble sort, the worst list that you can feed it is a list that's backwards. Sorted, but backwards. Like descending order list. That's going to take the longest possible time for bubble sort to sort. That's like the worst case scenario, okay? But anyways, it really depends on the algorithms. Some of them, the worst case scenario is not as obvious as bubble sort. And so what we care about is that scenario, because if we're using an algorithm and it's like mission critical, and we need to make sure that in any case, even on the edge cases, that the algorithm finishes within the expected time range, then that's something that we really need to make sure we look at the upper bound relationship. On the other hand, we have sort of the lower bound, which is big omega. And let me make sure I draw a nicer looking omega. just at least once in the whole class. And so I think that's better of what it looks like. You know, if you ever seen an Omega watch, that will be the logo comes from that. So yes, yes. I could show you. Nah, I don't want to be show off. Like, but I could show a little. I have like Omega logo somewhere. But anyways, so essentially that's the Omega. That's the lower bound, and the lower bound is the best case scenario per se. Again, there's more to it than that, but just for now, okay. So that's gonna be like the fastest that the algorithm can run in the ideal scenario. Again, easy way to think about that for us humans. If we're sorting, the best case scenario for us is we just look at the list and it's sorted, because typically, I mean, if the list is small enough that we can look at it within our eyesight, we can pretty much just check if it's sorted or not. Now, if we get a list that's like, you know, a stack of papers, then yes, it could be sorted, but we don't know, right? You want me to scroll up? Yeah, sure. There's big Omega. I'll move to the side so you can see that. But yeah, so that would be like the big Omega is the lower bound, the fastest that it can run, okay? And then finally, that leaves us with big theta, which is where we're going to pick up from today. But before I go to big theta, let's look even closer at this, okay? Because there is one point that I don't think I emphasized last time, and I want to make sure that I get that emphasized here, and that's the M constant, okay? So I'm going to scroll back up to big Omega, because we're going to talk about that, but I'll scroll back down to that later if you want. So big Omega, that upper bound relationship, right? Let's look at that formula one more time. So we got f of n is equal to big O, that's what the circle is, of g of n, right? And so as n goes to infinity. And here's the thing, that is only going to hold true that f of n is part of this big O class, and that's what this is saying, that f of n is part of a big O class. Now, what are the big O classes? Really fast, let me scroll back down, like these, n squared, and so on, right? And I'll show you more. But really, we're saying that f of n belongs to that class as n goes to infinity only when we can find a constant m that makes the g of n bigger or equal to than the f of n, okay? For all of the n's. So what we're really saying is this. F of n is indeed bigger than g of n, but we want to make it as close as possible to g of n, but still g of n has to be bigger than f of n with the m multiplied to it. Without it, f of n is probably going to be bigger, but with the m in there, we are making g of n times n bigger than f of n. And here's the thing, this is what I want to emphasize that I didn't last time. The m has to be a constant value that you can't change. So once you pick an m to be in that formula, it has to work for all scenarios of n. So if n is equal to 1, 1,000, 1 million, whatever number you want, positive, it still has to hold that relationship. So it's a little bit harder than that, you know, because like, suppose that, let's go ahead and throw some numbers in here, okay? So let me go ahead and copy and paste this beneath, and let's just throw in some numbers. And eventually this is gonna kind of lead into is what a certificate is. But before we go there, let's go ahead and throw in some numbers here, okay? So suppose that I said that the f of n function was equal to, and the g of n function was equal to, and let's go ahead and do, let's say g of n is equal to 5n, okay? So 5n. And then maybe, 5n plus 12. Yeah, let's do that, okay? So what I'm trying to do is I'm trying to pick a function f of n that is as close to this as possible, but then I can multiply to something constant, okay? So let's go ahead and pick an easy set. Let's say f of n is equal to n squared, okay? So what I'm trying to do is I'm trying to say n squared is less than or equal to g of n, which is 5n plus 12, times some constant, okay? So for all n's, okay? And let's start with 0 and work our way up. Okay, so let's say that let's say that you know, let's plug in this for maybe 0, 1, 3, and maybe 10. Okay, and let's see what each of these two formulas would give us. So let me scroll this down a little bit more, And so here we'll do the f of n, and here we'll do the g of n, okay, which is 5n plus 12, and then this one is just n squared, okay? So let's go ahead and do that for all of these, and just kind of look at these two functions, okay? We could graph them as well, but I don't have the technology set up to graph this immediately. So yes, I could have an open like matplotlib or something, but I didn't. So what is n squared? N squared is 0. So there you go, 0, and then 5n plus 12 is going to be 0 times 5 plus 12, so this is 12, okay? Then for 1, this is going to be 1, because 1 squared is 1, and then this is going to be 5 times 1 plus 12, which is going to be equal to 17, right? Correct me if I'm wrong, by the way. I'm kind of doing it quickly here. And then 3. So what is 3 squared? 3 times 3 is 9. This over here is 5 times 9 plus 12. 5 times 9 is 45, plus 12 is going to be 55, 57, right? Something like that. And then finally, 10 squared is 100, and over here, 5 times 10 is 500, plus 12 is 512. Okay? So, 5 times 3 plus 12. Oh, shoot. Yes, I totally screwed up. I took the power for some reason. Apologies there. Thank you for catching that. So yes, this should have been 3 here. So 5 times 3 is 15, and then plus 12 would be 27. And then 5 times 10 is 50, plus 12 would be 62. So good catch there. See, that's why I prepare you guys to be on top of things. Okay, so here we got a couple of numbers that we need to look at. So remember, the whole idea is that the g of n, has to be bigger than the f of n, right? And so does that hold true here? Does it hold true all the way? Well, or equal to. Here that holds true. Here that holds true. Here that holds true. But here it does not hold true, right? Because that is bigger. Okay? Do you see that? Do you see how that doesn't hold true as the numbers go bigger? And it's kind of obvious if you think about quadratic that this is only going to grow in a linear fashion, right? If we were to graph this, a linear fashion means a line, whereas the other one's a parabola. And what it really looks like here is more like this. And so this spot right here is where the parabola takes over and grows faster. And that is happening at some point between 3 and 10. You can get the intercept and figure out how much it is. We're not going to do that. We'll leave the math people to do that. It's probably somewhere around... probably like 4. What is 4 times 4? 16? No, probably 5. I think 5 is where it probably breaks. Asymptotically, the constant gets washed out at some point, no matter how big you make it. Yes, and I was going to get to that. So really, the only reason that this does not immediately grow faster, the squared, is because of the two numbers here, the two constants, the 5 and the 12. But as the numbers go bigger, those don't matter anymore. And that's why I was thinking 5, by the way, because 5 times 5, I was thinking about that. So actually 5 times 5 wouldn't work. So I guess 6 would be the bigger number that would be, that would eventually overtake this. Because at that point, this keeps growing. These are constant, so they eventually don't matter. And so at that point, you got to realize that it would be impossible to come up with a number that would always beat the n squared. So I could come up with and say, okay, I'm going to put in 1,000 there as my constant, okay? So that means that I multiply each of these times 1,000. The 0 is 0, that's fine. This will become 1,000, this will become 3,000, this will become 10,000, right? Well, guess what? That would work for now. But eventually, probably around the 1,000th number, then, or not even that, probably around the whatever 20 times 20 is 400, it's about maybe like 40 times 40 that's 800. So maybe like 50 times 50. By then, it would still not matter. So it would be impossible to try to come up with a function that with a constant there that would work, okay? So you can't do that. What does that mean to us? That means that if we're trying to find the asymptotic complexity of our function n squared, we can't do that in a linear upper bound. It has to be something more than a quadratic upper bound, okay? So what function could we put in g of n to make it match here? Well, easy, just put n squared, and bam, your constant could be just 1, right? So that's an easy one. But more interestingly enough, let's try and flip these two around and do it the other way around. So let's try and, let me highlight that. Let's flip these two functions. So now instead of trying to find a bound for n squared, let's try to find a bound for 5n plus 12, okay? The other way around, that's easy to do, right? Because we know that this will grow faster than this. But the question is, what constant do we need to put so it always holds true? So basically what we need to do is the same thing as shifting this up here so it always holds true. And technically speaking, it should look like this. So it's more like, it's right now it's like this. And so we need to shift it up like this. And the way that we shift it up that axis like that, you know, is, well, technically speaking, that will be an addition. So really what we're trying to do is we're trying to steepen it. So we're trying to squish it. That's more of what we're trying to do. So what we're trying to do, it's kind of hard to draw, is we're trying to steepen the curve by multiplying it like that. That's really what we're doing with the multiplication. Because technically speaking, shifting the y-intercept would be an addition. That's kind of what's happening with the plus 12. So what the plus 12 is doing there is it's shifting this up like that, okay? So that's what's causing us issues. And then the times 5 is making it steeper. So yes, basic math. But yeah, so in this case, what value do we need to put here as constant m for this to hold true? So if we bring this down yet again one more time, what does m have to be for this to hold true? What number do we have to put in here? And it turns out that, as I said, I think it's about 6. We can test it out. But I think that 6 could work. But guess what? 100 could work there too. I never said that you had to put the best possible value, right? So like, if you don't even want to think, you know, you're doing the test and you're just tired, you're just like, yeah, I think I'm going to say that m is equal to 100, and then this will hold true. And hey, you're not wrong. You're technically not wrong at all. Of course, if you're trying to sell your algorithm, you're trying to pick the lowest constant there, because otherwise you're, you know, it's like saying, hey, the top speed of this car, or the fastest acceleration from 0 to 60 in 5 seconds is going to be, or sorry, no, the acceleration from 0 to 60 seconds of this car is going to be at least 5 seconds, okay? That's what you say. And guess what? Your car's actually 4.9 seconds, but you want to be conservative and you say 5. That way you don't get angry clients coming back to you and saying like, hey, you lied or whatever, right? You could do that. You could also say 10 seconds. And even though yours is 4.9 seconds, if you say 10, you're technically not wrong, but you're selling yourself short, right? So that's kind of the other side of the coin with this asymptotic complexity. I can say that this function belongs to a class of O(n) squared because it's true. It technically does, because anything in O(n) squared or less belongs to O(n) squared. But I can also say that this belongs to class O of n, and then there's a constant which is 6. So I can go with either one of those. Of course, if you're trying to sell me your algorithm as super fast, I'm going to go with the guy that says this one. So you definitely want to sell yourself there. Does the word coefficient is 1 as well, since it holds true for all n squared? Yes. Yeah, I meant O of n. Yes. So yes, if you're sticking with the n squared, then I think you still need a constant of some sort, because it will not hold true in the beginning because of the plus 12. But eventually it will hold true. So I think in this case, you would still need to have a 6, whether it's n squared. And then you probably need like a 7 for n, actually. So here, let's do it. Let's actually do it. So if we were to stick with the n squared, because we're selling ourselves short, we still need a constant for the n squared. And it turns out that I think that constant is 6. Because, or actually, no, it's, let's see what it is. Well, if we're looking at the squares that we did already, this will give us 17. And then this will give us 9. And 9's already bigger. So really, yeah, so we only need, I think, 1 for that one. No, I'm looking at these numbers. So times 2, times 3. I think times 3 would do it. No, because we got the 17 here. So I think we need to have 17 to get this working. As long as you have 17, it would be okay for all cases. So that we can get to the end, to the first case. Yeah, I think 17 is the one that we need. N has to be equal to 17, just so that the case where n is equal to 1 works. Because if n is equal to 1, you know, we got 17n squared, and that is going to be bigger than or equal to 5n plus 12, which again is equal to 17, right? So in the case where n is equal to 1, right? So we need to have the m be 17 just so that we can get the case of n equals 1. Of course, if n is equal to 2, we can lower the constant. But remember, the thing is, we need to make it work for all positive numbers. And so because of that, we get that special case. And we're like, you know. But yes. So yes. So it will, I mean, the n equal to 1 would work for all cases, but it's not about whether it will surpass it. It is that it has to be an exhaustive thing. So it has to work for all numbers. It's not enough to say, well, yes, eventually this will work out. No, it's more of like it has to work for all numbers. So that's the kind of only trick about m. You need to find an m that works for all cases. That's the very important symbol here that you're looking at, for all n, okay? That is greater than n equal to n0. So it has to work for all n. Okay, if you were to put it here and change this to n0 to make it like n1, then you can change your m. But in this case, the math formula, the way we wrote it, it says it has to work for all n. Okay, so does that make sense as to why I have to pick 17 there and I can't pick a smaller number? I hope so. Anyways, while you guys answer that, let's go ahead and figure out what the number would be if we're trying to use n instead of n squared. So in this case, we got 5n plus 12. And what we're trying to do is we're trying to find the m so that we can do m times n, okay? That one I think, like I said, is something like 6 or 7. So if we pick 6, then, oh, that wouldn't work. I think we're gonna have to pick 17 as well for this one too, because of the case with 1. So yeah, we're gonna have to pick 17 as well. So it is gonna be the same thing because of that n1 case, okay? So yes. No, you're right. So n0 is the first member indeed. Why is the chat not showing up? Or maybe it is, I'm not catching it. But yes, it has to be for all cases, okay? Including and then by n0, we're not saying it's the first member. N doesn't stand for the index of the members. It stands for the size of the input. That's what it stands for. So we're saying the size of the list that we're sorting, for example. If we're sorting 10 numbers, n is equal to 10. If we're sorting 1 number, n is equal to 1. If we're sorting 0 numbers, n is equal to 0, which is kind of a weird scenario that doesn't really work, but whatever. Okay? So, yes. Yes, so n is the size, okay? Of course, you can do your own modifications of formulas and things like that, but this is kind of what is the standard, okay? So, anyways, I just wanted to make sure that we were on the same page with that m. It has to be constant. You can't just change it as you see fit. You always have to fit it, okay? And that actually brings us into a topic known as certificate, which is exactly what we're doing. Is when you're trying to prove something is of a certain asymptotic complexity, you want to give that m value to the people, basically. You want to show that m. And so maybe we'll go into that next before we talk about theta. So we already saw that you can analyze some basic code like this loop here, and you can analyze that and you can give a time complexity, right? You can give n, you can give n squared, and so on. Over the weekend, I'm going to release an assignment. Well, I'm releasing it probably tomorrow or today, and then you'll get to do it over the weekend. An assignment where you'll be looking at a bunch of these codes. I think it's 4 of them. And then you will analyze the time complexity, and then you will just copy and paste them into the terminal, run it experimentally, and confirm experimentally that your asymptotic complexity that you mathematically calculated ahead of time matches. Well, mathematically it's basically like n times n, but you know, mathematically still, that it matches. Okay, so that will be the assignment. It'll be a cool assignment because it's like very basically no coding. You're just copying and pasting code and maybe adding like a variable to count things with. But that'll be the assignment of the weekend. And yeah, so you'll get to practice doing more of these. But basically, you know, just understand the basic rule of thumb is if it's a loop, you multiply times n. If it's a nested loop, like if you have one loop inside another loop. So if you have, like, for example, for I and R, and then in here you have for J and I, and then you have for K and J, something like that. Okay, so you got 3 nested loops in there, range 4 loops. This is a 3-dimensional array you're working with or something. Okay, in this case, each of these is a size n, then this takes n cubed. So basically, if the loops are nested, you multiply them together to get the asymptotic complexity. So this will be n cubed. Okay, if the loops are in serial, so like if you have, for example, let's say you have 2 loops after these loops. They're not nested, they're afterwards, like this. In this case, it's addition and not multiplication. So in this case, for example, it would be n cubed plus n squared, okay? And let's say maybe you have another loop on top of all of this that is just that is not nested, it's just in serial. See, I'm doing that by showing you the tabbing. This is not tab, whereas this is tab and this is tab. In this case, it would be like saying n cubed plus n squared plus n, okay? So this also brings up another point. If you get a time complexity of this sort, yes, it's a good idea to share it, but it's also important to understand that this is all really kind of represented as just O n cubed. Why? Because, again, it comes back to this idea of a constant, that you could find a constant big enough that you could kind of work around this. Now, this was a little bit trickier because, technically speaking, it's more than one constant because of the n squared and n being related to n. So you have technically like constants a, b, and c in front of each of these n. So it's a little bit trickier than that when we have multiple n pieces in your formula. But still, kind of trust me on this, that you still represent that only as the biggest of the exponents. So in this case, you pick the n cubed. The only time that you really kind of leave the lower ones are the subcategories like, where is that? Did we write those? Yeah, these guys. So the only ones where like you kind of care about leaving smaller values is this one. And maybe even this one sometimes, okay? N squared log n and n log n. Those are actually worthwhile keeping in. You don't just represent, because I mean, otherwise you could say this can be represented in terms of n. And it's technically true. But what happens is that a lot of really big algorithms are in the n log n category. And we actually, it's actually a big enough difference between n log n and n squared, and between n log n and n squared, that we like to have that in between. But like, and even between n squared and n cubed, n squared log n we want to have. But when we get to n cubed to n fourth, it doesn't matter if it's n cubed log n or if it's n cubed plus n squared. It doesn't matter at that point. N cubed is like on the crappy side of algorithms where we're like, oh, that's not that good. But some of the things we just have to do like that. But n cubed is like around the time when like you're like just like, well, that's nice that you found a solution with n cubed. Now, can you find a solution that we can actually finish before we're all dead, basically, and the universe has expired, kind of thing. So yes. So we have a question. What if the for loops don't run the same amount of times? That's a good question. So let's just say, for example, and then I'll get to the question beneath it as well. So first I'll answer them kind of in order. Let's say that we have a loop. Let's actually write some code maybe for this one. So for int I is equal to 0, I is less than n divided by 2. Okay? I plus plus. And then maybe we have another loop. First we'll have 2 0 and then we'll have 2 parallel. That one runs the same like that. And maybe we have a third loop, and this one only runs, or maybe this one runs 2n times, you know? Or maybe this one runs 3n divided by 2, okay? And then as another example, we will have the same exact code, but nested, okay? Because that we could have run into something like that. Okay, so maybe this one is nested. So it'll go off the screen, but you get what I'm talking about, right? It'll, you know, like that. We might be able to recover some of it. Like that, okay? So let's see what happens in these cases, okay? So in these cases, if it's sequential, you add them together. So instead of this being n, it just becomes n divided by 2 plus 3n divided by 2 plus 2n, and you just do some algebra. So basically, just add these two together. So this becomes 4n divided by 2 plus 2n. The 2's cancel, the 2 cancel there. So this becomes 2n plus 2n, which becomes 4n, which at the end of the day is the same thing as O of n. So you would just say O of n, okay? Again, this is that constant m. What is the constant in this case, by the way? That's easy, it's 4. 4 would be the constant that would fit. Our m is equal to 4, okay? Again, I'll show you a little bit about certificates, which is basically that, but more formalized in a second. In the other example where it's nested, you just do the same thing, but in this case, you're multiplying them. So you do 3n2, and then you do 2n. Okay? In this case, this becomes 6n cubed divided by 4. We can simplify this, I guess, to just say 3n cubed divided by 2. Okay? So this really becomes just n cubed. If you're curious what the m would have been here, it's 3/2. Done. Okay? So that was the first question, and now we go to the second question. What if you have an array, and you're looping through it from 0 to the end, and you have a nested loop that is only looping through half? Would that still be n squared? Okay, that's a good question. We kind of partially answered that. So if you have, to make sure I get this right, if you have an array, and you're going from 0 to the end, but you're only going through half of that, what you're really doing is you're doing n squared divided by half. So really, it's still going to be n squared in time complexity, and in case you're curious, the n would be 1/2. So yes. When will the time complexity be n times m? So the only time that you don't analyze the time complexity in terms of a single variable is kind of edge cases in terms of algorithms, like when you're dealing with things like strings and stuff, that you really want to represent an algorithm, not just in terms of the number of elements, which is usually what n stands for, number of elements, but also within those elements, the length of the elements. In that case, so string alignment algorithms and multiple string sequence problems algorithms are going to have an n times m. I will tell you in this class if there's ever a scenario like that where we're considering things as more than one variable, but most of the time it'll be a single variable. But in the case there's more, it's okay. You would just say n times m or n times m squared. I think when we look at some of the graph ones, we like to consider things in terms of vertices and edges. So you'll see v and e in the big O thing. So it'll be O v times e, but only in those cases. Again, it's really up to you how you represent these things. Typically what you do is if you come up with an algorithm that you think is better than the state of the art, then what you do is you look at the state of the art and see how they're measuring their stuff. And then you take that and then you measure it on the same standard yours. Okay? So that's kind of what you do. In the case of the example, the nested loop running from I to j to n instead of I to 0, then you use summation notation, right? Well, I kind of had each of the variables I were local. So like this I plus plus is not modifying this I, so they're not doing weird things there. If you're doing from I to j instead of I, not sure what you mean. So let me read it slower. In the case of the example, the nested, no, I mean for like n is equal to 0, and then the nested is from I to j. Oh, I see. So you're doing kind of like okay, I see. So the kind of algorithms that run for like the first time, kind of like you run that, and then the second time, the inner loop is, the second time you're running it, if you're running on this, the inner loop is only running on that, and then the inner loop is only running on that, and then the inner loop is only on that. So okay, I see what you're saying. Okay, that's a tricky one. So I gotta think about that, how that would work. So the outer loop is gonna run n times. This gets into recurrence relations actually. This is a good one. And then the inner loop is going to run n minus 1 times. And how many inner loops do you have? Just one? So in that case, this would actually be solved by a recurrence relation, which we'll talk about in a while, would be n minus 1 times n. I think that would be it. A Gaussian sum. So in this case, this, I think the recurrence relation for that is actually n log n. But I'm not sure. We'll solve that in a little bit. I think I have the, if I peek into my answers, I think I might have that. Actually, it could be n squared, but let me just, let me cheat and look ahead, because I know that's one of the ones that I actually make you guys do. So let me cheat ahead and see what the answer is to that. I thought I had it here. Ah, oh, that one's +1 and -1. So I don't have that one here. Okay, so we'll have to solve that one actually to figure out what it is. So is it n squared? I don't. Well, here, let's try to, so the first time it'll be n. Let's say n is equal to 10, and then kind of analyze the numbers. So the first time the n one is going to run 10, and the second one is going to run 9 times. Then it's going to run 9 times, and then 8, and then 8, 7, and then 7, 6. So you're only missing one run from it. So you're only running, I believe, half of these. So I think the actual value is 1/2 n squared. I think that's the actual the solution to that, which would still be indeed n squared. So I think that's it. But we will figure out how to solve these in a little bit. I could also, if you want to Google Master Theorem, you can solve it very quickly. So yes. Okay. So what is this recurrent relation stuff I'm talking about? We will find out in a second. But going back to our code here, we still need to talk about theta. We still do. But now I am going to talk about certificates. Okay, let's do certificates next. So suppose that you came up with these asymptotic complexities of n cubed, n squared, log n, whatever it is, right? You came up with these, and now you want to sort of prove what this n value is that really shows that you're really in the n cubed category, for example. Okay, that is what certificates are useful for. So let me find an example of the syntax of certificates. Here we go, to show that. So what you want to do is, suppose that you came up with the following answer. So you came up and said that the answer, well, here, I think let's take one of these. So 4n, we came up with a 4n, right? So what we want to do is we want to say that 4n is basically belonging to a certain asymptotic complexity, okay? So we're going to say that E symbol, which means element of. So we're going to say that 4n is an element of asymptotic complexity time n. Okay? And so again, we need to do is we need to put that in terms of f of n is less than or equal to m times O of g of n. So what that really converts to is saying 3 of n is less than or equal to c times n. Okay? So now what we really need to find out is what that c is equal to. And then here's where we have the freedom to change that n sub 0 thing. Because remember, before it's like for all n starting out from n is from n0. And so we have the ability to kind of limit ourselves on that. So now we can say, okay, we know that things get kind of weird with that special case of n is like 1. So let's go ahead and just do greater than 1. That way we can make our lives a little bit easier. Or we can stick to being 1 too. So what we really need to do here is we need to figure out what c is equal to in this case. Okay, so the easy math way of doing this is you can just solve for c, right? Because I mean you could divide both sides by n and eliminate n on both sides, and you end up with 3 is less than or equal to c, and then just pick basically 3 or greater. Okay, and once you pick a c, which is your m, what you usually do is you do a little box. You say what c is equal to, and then if you have any constraints on the size of n, here's where you can put them. So I could say n has to be greater than 1, or you could put n has to be greater than 2, whatever you want. That is what you have the power in the certificate, okay? So now let's go back and look at the original one that we did. I think it was 5n plus 2, okay? So let us say that we want to represent this as an element of, I don't know, O of n. And by the way, again, I want to emphasize this. If you say something is of asymptotic complexity n cubed, this is an asymptotic complexity of n cubed because it's anything and below. So by that logic, I want to see if you guys follow this. Any algorithm that belongs or is an element of the asymptotic complexity of O(n) squared is also an element of the asymptotic complexity of O(n) cubed. Does that make sense as to the why that would be the case? Okay, cool. I wanted to make sure. As for the question as to wouldn't it be c is greater than or equal to 2, 3 is literally the same thing we wrote here. This, if you convert this into C++, that is written like this, which is the same thing as that. That's just flipping the sign. So you're right, but at the same time, this is right too. Okay. So yeah. But yes. So good. That's good that you guys understood the thing. Going back to the thing about any algorithm being an element of O of n squared is also an element of O n cubed. Similarly, any algorithm element of O n, O log n, O n log n, they're all elements of O n to the fourth. You know. So yes, it's very important. So I'm not gonna do that, but I could ask a cheeky question and ask, why is bubble sort an element of O n to the fifth? And then you could be like, people could fool and say, no, it's n squared. But then I come back and say, yes, but n squared is also part of n fifth. Why is c equal to 3 in the box? Because when you're doing a certificate, you want to pick a number. We know that any number bigger than 3 would actually work in this scenario. But in terms of a certificate, we want to have a number. You got to pick a number. Like actually just pick a number from the group here. So 3, 4, 5, anywhere up to infinity potentially, but you still need to pick one number for the certificate, okay? Because we want to have an actual value for m. We don't want to have a range of numbers. We know that technically speaking, any number bigger than 3 would work, or 3 itself, but for the certificate part, you pick actual numbers. So that's why you see 3 there, and you don't see me put in like greater than 3. So I see now what you were saying when you asked the other question. That makes more sense now. So yes. Okay, so yeah. So basically, I guess it's a good thing, because I mean, if you're really lost in the test, you can hope for the best and put a really big number in C, you know, because you can expect that I'm not going to ask big numbers, right? But you know, don't be cheeky like that. If you know better than that, then show me. Be proud of your answers. But anyways, okay, so let's try to do this with this one. Okay, this is a little bit harder, quote unquote harder, you know. So what we want to do is we want to put it in the same syntax here, and the test is open notes. So I mean, you know, prepare your notes ahead of time, I suppose. So what we want to do is we want to convert this into 5 of m plus 12 is less than or equal to some magical c times n. Again, I called it c, but it's m in the above thingy over there that we did. Okay, so again, in your head, just ignore that it's a less than or equal. Just think of it like an equal sign so that you can remember the math. So here it's a little bit trickier because you got the 12 in there, which is kind of a pain. You can't just divide everything, but you can sure as heck subtract. So yeah, let's go ahead and do that. So let's just subtract 12 from this, 5m from this side. So 12 is less than or equal to c of n minus 5n. Okay, so we got that so far, and then yeah, let's go ahead and divide this whole thing by 5. Okay, so here we got 12 divided by 5 is less than or equal to a constant divided by a number is just going to be some constant again. So we don't really need to worry too much about it, but I'm gonna leave it here just to be safe, okay? Just because it's been a while since I've done math, so might as well not screw things up. I do believe that you can just ignore it, but still. Okay, so what am I doing wrong? I'm screwing up something here. Does anybody have any suggestions about what to do here? I'm trying to remember how to cancel this, but it's my head is rusty. Oh, I think I know what I screwed up here. Hold on. I should have factored out this first. So let's just go ahead and put c minus 5 divided by 5 times n. Okay? That is equal to the same thing as that, right? Yes. And so now we can say this is less than or equal to 12. And so now we can go ahead and bring that over. No, no, I'm not sure. Factor out, factor the n out. Factor the n out. Okay. Well, if I factor the n out, I'm going to get it into 12. That's the problem. So if I factor the n out here, then I'm going to get 12 divided by n. You see? So I divide everything by n, by n. I am going to get 5 plus 12 divided by n is less than or equal to c. Hey, actually that might make things a little bit easier. Okay, I can't think of the math, so what we're gonna do is we are going to get rid of the 12 for now. Okay, so we're gonna say 5n is less than c of n. Okay, that we know can be solved with a 5. Okay, we know that c can be equal to 5, but then 12 is an issue. Okay, so when does that 12 stop being an issue? It stops being an issue after n is equal probably to 3, I think. I know what we can do here. We can add a second c for that. We can add a c1 and a c0. Yeah, we can do that. Okay, so what we can do in this case, just to avoid a headache, is we can add a z0 and a c1. The z0 is for when n is to the power of 0, and this is for n to the power of 1. In this case, we can make n1 be basically 5. Or sorry, z0. Oh, it bothers me that the numbers aren't matching. Let me match them. So this will make this a z1. And this makes a z0. Okay? And then that way things match and look prettier. So now we can say that c1 is equal to 5. And that is equal to 12. We can do that. Or if we just want to get rid entirely of the c0, then we can make it 6n. So we can make it 6 here. That is going to be, for the first one, it's let's say we make n greater than like 3. Okay? So in this case, if n is greater than 3, it would be 4. First number is 4, right? So if we make 4 times 5, 4 times 5 is 20, plus 12 is 32, right? When n is equal to 4. On the other hand, 6 times 4 is 24. Okay, so it has to be bigger than that still. Maybe we make this c and 10. Let's go with 10, whatever. That will work for sure, because 10 times 5, or sorry, 10 times 4 is 40. So yeah, that'll work. So then we can get rid of that and keep one single constant. So there you go. That's a valid certificate. It wasn't very mathematically calculated, but I really can't think of how to remove the n there. It's probably a very easy way, but you know, whatever. I'll leave that as an exercise for you guys to figure out mathematically, okay? But as you can see, there's a lot of certificates. Now, is this the best possible certificate? Probably not. I could probably come up with a lower number than C being 10. Because what I'm writing here is I'm saying 5 of n plus 12 is less than or equal to 10 times n, okay? For all n where n is greater than, what's the right syntax for that? Let me write it in a pretty way. For all n greater than or equal to n3, yeah. For all n greater than or equal to n3, okay. N4 technically, because I am saying greater than. Or I can just switch this to greater than and keep it at 3, like that, okay? So this is what I'm essentially writing right here with the certificate, okay? How do you get the n3? I just picked the number that was big enough that would make this work. Because if I pick n2, it's not going to work, I think. So if I want to make that lower, let's say, okay, fine. Let's say that, well 1 is never going to work because of the plus. We're never going to get 1 working. But we can do n greater than 1, you know. In that case, we need to make sure that 2 times n is bigger than, that 2 times some number, which is whatever our constant is going to be. So c times 2 has to be greater than or equal to 5n plus 12. Okay, so what number is that going to essentially be? And again, this is 2 right here because we picked that. So in this case, 2c is greater than or equal to 10 plus 12. That is going to be 22. So what number makes that right? 11. So we can pick 11 there. So wow, it's glitching out. So I believe that is also a valid certificate. That's probably a nicer quality one too, because it's n greater than 1. So what we're saying is any number bigger than n1, so n2 and on. Okay. So really, you can pick whatever you want. Ideally, you want to you want to make n as small as possible, and you want to make everything else as small as possible. Because again, it's like rounding up your top speed time 0 to 60 from rounding from 4.9 seconds to 5, because you're kind of iffy about finding 4.9. It's kind of like that. So you want to give the best value. So the second case is much better than the nicer one, but they're both perfectly valid values. Okay. When optimizing the certificate, would it be better to try to aim for a smaller c or a smaller n? That's subjective. It's really subjective. I think I would say a smaller c, to be honest with you. Yeah, I would go with that. But again, it's really subjective because I mean, what you're really saying is that your algorithm is great. It's definitely fast the bigger the data you get. But you have these weird cases where it's so small data that it's not going to be good because it's slow, because it's so small data. So I would say optimizing the C is better than optimizing the N. But again, it's really subjective. So in my case for grading, either one is fine because we're not. But if you're actually using this in practice and you're trying to prove your algorithm is good, then I would actually show both best case scenarios. Optimize the C and then optimize the N. And show them both, and then be like, there, guys, there, I did it both ways. Pick whichever one you want to compare my thing against. So yes, I got lost. Why do you have to see 10? Are you still lost on that? If so, I got the 10 because I'm trying to prove that this is what I'm trying to prove here. Let me use a different highlighter for that. I am trying to find a solution to this thing right here. 5n plus 12 was c times 10. I need to pick a number in c that is going to make this true. And if I pick 10, then it holds true as long as n is a bigger number than 3. That's what I'm doing. I'm doing algebra basically, without doing hard algebra because I couldn't remember how to factor out an n. That's sad, but it's been a while. So yes. Okay, so that completes certificates. Before we jump on recurrence relations, at least as a start for today, I would like to remind you, by the way, yes, this is kind of all over the place a little bit today, but it's okay. Next Monday is Labor Day, so there's no class. I mean, I would have no problem with streaming class, but I checked and I'm not allowed to force you guys to watch it, so therefore I can't have class. So no class on Monday, okay? So the next time we will have a live stream is on Wednesday. Just FYI while you guys are here. Okay, going back to this. Before I show you what we have at the time complexity assignment due next week, you probably have it due see, I'm not in a rush to make that due anytime soon because the assignment after that you are not going to get for a while. So that'll probably be due in a week and a half or something, just because there's no rush in getting it done. The third assignment, we got to get through all the recurrence relation stuff first, which is going to take at least a week. And once we get done with that, then we start talking about stacks and queues and linked lists, and then I give you that assignment. So, there's a big gap. In fact, I was tempted to kind of switch gears, show some sorting stuff, so you guys can get started on sorting and then come back to this. But I was like, no, I'd rather finish this. So, yes. There's a bit of a lull at the beginning of the semester with assignments. Don't worry. There'll be a time when you wish you had this lull again. So, yeah. Okay. So, all right. So, we covered big O, big omega. We still got the big theta to cover. So, let's actually hop on that and cover that real fast. Okay. So, big theta. So, going back to the definitions that we did, we said that the upper bound is big O. The lower bound is big omega. But then, what is this big theta? What is that? Question mark, question mark. Okay? It turns out that big theta is something in between, and that something in between is kind of ambiguous. So for that, we can go ahead and turn to the math to tell us and solve our ambiguity as to what big theta is. So in practice, big theta is not the average. It's an easy way to explain it, and it's a nice word to use, but it's not exactly true, okay? It's kind of like the average. It's like, it looks like an average, it tastes like an average, but it's not an average, okay? Kind of like that. You ever seen that ad, like, smells like chicken, tastes like chicken, it must be chicken? In this case, it smells like chicken, it tastes like chicken, but it's not chicken, it's big theta, okay? So basically, big theta. Okay, so let's look at the math. So we're saying that the FFN, the function of big theta, is equal to oh, by the way, theta, the way you draw theta, nice theta, I suppose, is a little sort of curve, like italicized O, and then the line in the middle like that. The line should be kind of inside only. So that's how you draw theta, by the way, okay? But of course, you know, that's the nice looking theta, and then that's like my ghetto theta, okay? So looking at theta, what theta is theta is defined as the function in between big O and omega, as long as there exists a constants k1 and k2 that sort of map this function in between, okay? That's sort of the short explanation of that. That's what I expect, like in a test or something. What it really means is, looking at the math here, when f of n, which is our theta function here, is equal to big O, and it's also equal to omega, you know, if those two hold true, we kind of update our equality thing. So before, you know, we're saying f of n is, you know, greater than or equal to m times g of n for all n, basically, for big O, and then for big omega, and then for big O we have is less than. Here we have, but we kind of squish them both together. We are saying that g of n is going to be less than f of n, which is less than, I guess, the second g of n, okay? And so we are saying that we can find a function, an exact function that fits in between the upper bound and lower bound. And we have a k1 and a k2. K1 and k2 are log m, but we have two of them. But this is a lot harder to do because we're trying to find two constants that are going to sort of tighten the boundary, okay? So if we look at the graph, you know, let's revisit this graph again from last time. We have time on the y-axis and size of, like, the data on the x-axis, okay? And by size of the data, I am talking strictly about n, okay? N growing in size, okay? And so we are saying, obviously, the longer something takes, the slower it is, right? And this might be a little bit misleading in terms of how the graph looks, but that the slower something is, the higher it's going to be in our graph. The closer it is down, the faster it is, right? That is why the red line is going to be and I'll even write it here, big O, okay? That's the big O because that's the upper bound. We're saying that it's never going to be slower than that, okay? As you can see, it should grow. The bigger the size, the more time this should take, right? Unless it's a constant big O, even if it's linear, it should grow linearly. So the more n, the slower it is. That makes perfect sense. If it was quadratic, then it would look more like this. Oh no! Oh, I thought it died like yesterday. So if it was quadratic, you know, it would look something like that. In fact, here let's actually draw a quadratic one. So let me pick different colors. So maybe this is quadratic, and then the lower bound of this formula happens to be linear. And then the real experimental data it doesn't always have to be precise, so it might be something like that, okay? But we're saying it's kind of in between, okay? It can never, the purple line can never go over the red line or beneath the blue line, okay? So in this case, maybe this is like n squared, and then this is maybe like O of n. And then we have, we just have the real function, okay? So the function maybe is something like maybe n squared divided by 4, something like that, okay? plus 2 something. I don't know. Whatever. Maybe not that plus 2 because then we got to shift the other one. So, yeah. Okay? And so what I'm saying is it can never cross either of these boundaries, okay? So that will be for quadratic. But let's go back to the sort of the linear example, okay? So for the linear example, we're saying that it can never be slower than that red line. It can never be faster than the purple line. It's in between, okay? But that in between, as you can see, goes all over the place. Big Theta says, hold on a second. We can actually find a function, a line, could be a squiggly line, but still a line that can be basically mapped exactly to how long the function is going to take. Now that's a lot harder to do again because like you have to find something that is an exact match per se, okay? And that's, to build that line, you need to add in 2 constants instead of 1. And those 2 constants are going to be K1 and K2. They could have called them M1 and M2, but for some reason whatnot, they decided to call them K1 and K2, okay? So that's why you see K here instead of M, maybe to separate them, okay? So we're saying that G of n times this constant K is going to kind of be your lower bound, and then G of n times K2 is going to be your upper bound, okay? So that's kind of what we're saying. We're saying that we're basically mixing both the constant from the big O and the constant that we found from the omega. And as long as we map these two, and this holds true, then we have essentially found the big theta. So big theta will always be in between. Now, there are some algorithms that big O, big omega, and big theta are all the same exact function. Bubble sort. There you go. Bubble sort in the inefficient way is O(n) squared for big O, big omega, and big theta. There are other algorithms where big O and big theta are typically the same thing, and big omega is different. That happens a lot. Off the top of my head, probably not merge. Which one would be like that? Maybe selection sort, or is it selection or insertion sort? One of the two. I think selection sort. One of the two omega is n, and the other one's n squared. So whichever one is n, you got big omega is n, and then big theta and big O are n squared. I think it's selection sort, but it might be insertion sort. Here, quick Google. Oh, that brings me to this chart. So I have a chart on Canvas that I want to show you real fast. It's available on Canvas. It's not my chart, of course. I found it on the internet, and I've shared it with students because I think it's pretty useful. And so you can look at a bunch of algorithms. A lot of these we're going to cover in class, and it's a good sort of a cheat sheet to have and study from. And here's selection sort. So it's actually insertion sort, the one that we were thinking of. So here's an example of insertion sort where big omega is n, and then big theta and big O are both n squared, okay? What you typically don't see, but may see actually sometimes, is when the big omega and the big theta are the same, but big O is different. But quicksort is the one exception to that. Quicksort is big omega is actually n squared. Yes, the worst case scenario of quicksort is as slow as bubble sort. However, it's very rare to happen that. And essentially, quicksort is going to be faster than merge sort, even though merge sort has a lower theta, omega, and big O. So, yeah. So as you can see, it matches. And what that really means graphically is that the line, the constant that you found to draw the line for theta is either closer up or closer down or right in between. Some of them could be different, but it's very, very rare to see that where like omega, theta, and big O are all different. Theta is usually goes one way or the other. It's very rare to see it in the middle somewhere. Because again, it doesn't mean that they're exact same. Again, there's these constants involved that you kind of get rid of. But we're still saying it's going to go with one way or the other, okay? So, yes. Questions on that? Does that make sense? Let's look at this little graph here. This is kind of cool. So there's a couple of other asymptotic complexities. We talked about constant time, which is O of C or O of 1, O of 74. They're all constant, but we usually say O of 1. There's log n, which is pretty low to the ground. It's kind of squished here. It's kind of, I guess, where the green line is. That's log n, technically. And then we have n, which is linear relationship. And then we have n log n, which is more than linear, but not quite quadratic. But it's still kind of curving up. Then we have, somewhere in here, we would have technically bound here we have square root of n, and then here we could have n log n, and then from there we could have n log n. You see that sometimes. Then you see n squared, n cubed, n to the fourth, n to the fifth, all the exponents. And then you get to these two sort of extreme classes that are called exponential. And so this is exponential right here. You have a base number, 2, 3, 4, whatever, but the n itself is an exponent, okay? So that's very different than where the base is the n and then the exponent is a constant. Like n squared is always a 2. So you could have 10 squared, 100 squared, but it's always squared. That's a much smaller number than having a base that's a constant and then the exponent being the n. That is insanely big, because think about it. 2, just 2, okay? 2 to the n power. 2 to the second power, no, not bad, 4. But then you go to 8. Then you go to 16. Then you go to 32, 64, 128. And then you very quickly, it just goes all over, right? 10. 10 to the first power is just 10. 10 to the second, 100. 10 to the third, 1,000, right? And so on. And so essentially, what is happening is it's going to go way faster than any quadratic function that you could think of, or any exponent function that you could think of where it's the base that is the end, okay? And you can even find something that grows even faster than that, and that is quadratic, okay? Oh, sorry, oh, no, factorial, that is factorial, which is the last one that you see up there. Factorial is going to be the one that grows the fastest. Factorial is basically saying if n is equal to 5, you do 5 times 4 times 3 times 2 times 1. If n is equal to 8, you do 8 times 7 times 6 times 5 times 4, and so on. That just, it goes insane. So in practice, what does this mean? In practice, it means that any algorithm that is bigger than n cubed is too slow for our purposes. Algorithms that are in the exponent range are practically unachievable in our lifetimes. Like, we could leave this running in the fastest computer in the world and it would not finish before we die. Like 200 years from now, it will still be running. 1,000 years from now, it will still be running. The entire universe could expire and it could still be running. That's how slow something on the exponential or factorial range would reach. Some algorithms that have been developed to solve some of the passwords that we use. There are algorithms that can solve the password, that can crack it per se. But those algorithms take exponential time, or something really high in terms of the powers, like n to the 8th power or something. At which point it is, for all intents and purposes, impossible to crack that password. Now you can brute force it and things like that, but we're saying in a algorithmic way. So what do we do then if we have an algorithm that is like super slow like that? There are other approaches that you can do to try to solve it. There's heuristics, which involve a certain level of guess and a certain level of error. Because here's the thing, all the algorithms that I'm talking about right now, we're saying that we are guaranteeing a solution that fully works in this amount of time. That's what we're guaranteeing. However, there are other algorithm types, these are heuristics, that can get you a guess that may or may not be a solution. And this we'll talk really closely into the semester when we talk about like P versus NP and that kind of stuff. But it's very easy to verify whether the solution is right or wrong. But at the end of the day, all we're getting are guesses, okay? And guesses is not the same thing as guaranteeing a result. And so heuristics are there to kind of help us out in that range of algorithms. But ultimately, the ideal case is to have an algorithm that for sure will give us a solution. And if that's the case, n cube is going to be around the time where if you solve a problem, but it's slower than n cube, it's useless. Because again, think about it. We're thinking big numbers here. We're not thinking like, oh yeah, I have an algorithm that can solve this 10 numbers, you know, with n to the 20th power. Yeah, sure, whatever. Even 5 times to the 20th power is not too bad of a number. You know, it's still pretty big, but it's not too bad, right? But solve it on a real problem where you have like thousands of numbers. Now we're talking something that is like impractical to do, or impossible outright. Okay, so as the last thing to talk about this is a little bit about space. Okay, so we've really been focusing on talking about time, but all of the stuff that I said applies to space. Big O, typically you don't care about big omega or even theta when it comes to space, because like the lower bound of space is kind of a weird thing to think about. Usually space is pretty much the same all the way. So usually you will only see the big O when it comes to space. Even in this chart, you will see that there's a space complexity, and it's just talking about the worst case scenario. And that's really because, you know, we don't want an algorithm to crash because it ran out of space. So we really mostly just care about how much space do we really need in the worst case, which tends to be usually the same as the average case or the best case. That space doesn't vary as much. It's kind of a fixed thing most of the time. With some small exceptions that we may talk about, like the hashing is the biggest one that I can always think of. So how do we feel about asymptotic complexity? Big O, big omega, and big theta. Do we understand what these mean and how they are used for algorithms? Do you understand what certificates are? Mostly good. Okay. I really try to emphasize and go slow and repeat myself a lot, mostly just because I want to make sure that you understand this, because as we visit all these algorithms throughout the class, as we look at quicksort, bubble sort, AVL trees, all these things, we are going to be analyzing their asymptotic complexity. And of course, if we don't know how to do that, if we don't know how to look at what asymptotic complexity even is, then, you know, you guys will be lost on that. So that's why, you know, really, it's kind of like, a lot of the classes are built on each other, you know, they're algorithms that we talk about and then we move on. But the one thing that is shared upon all of them is that we will look at their asymptotic complexity. We want to make sure that as we're looking at it, that we know, when I tell you like, yo guys, this algorithm takes n squared time and this algorithm takes n, which one's better? You automatically are like, whoa, the n one's better, right? This is the kind of stuff that you have to start to look at when you come, see, you reach the stage in the CS career, I guess, in the CS degree, where it's not enough anymore to just solve a problem, but you also want to make sure that you solve it efficiently. And now with this asymptotic complexity, you can actually analyze and see just how efficient your algorithm is without even plugging it into a computer. And that's kind of, I mean, yes, at the baby level, you know, we looked at some functions, you know, we haven't even looked at an example of a recursive one and things like that. But at the baby level, you can see kind of how to do that, right? You know, you can see your loops. You can now kind of see basically just the loops right now and some functions maybe. But now the second side of the coin is, how do we analyze it a little bit deeper, or how to look at code that is not necessarily as trivial as loops that we can just see like, oh, okay, these loops are nested, so this must be like n cubed or something. That is where recurrence relations comes into play. When we're looking at recursive code and we're trying to represent how to measure this code in terms of like how the time required to solve a problem in terms of the size, that is when recurrence relations are going to be used to determine the runtime. Okay, so recurrence relations are used to determine the runtime of recursive programs. And guess what? Recurrence relations themselves are recursive. So we're going to use recursion to solve recursion, or better yet, we're going to use recursion to figure out how long recursion takes to run. It's a little bit of a weird concept, but that's kind of what we're looking at. And I thought we would get to it today, but that's okay. We have a lot of time, and next week we will dedicate the day to talking about recurrence relations in detail. And then if I have time, I will show you how to use the master theorem. I did that last time around, and I was really happy to do it. I don't know if we have that much time to show it, but if not, they cover that in 477. But I still would like to show it because, like, it's kind of like when you learn the hard way of doing things and then you learn the easy way. That's kind of what it is with recurrent relations. You learn the hard way and then you learn about the master theorem and you're like, wow, that's just so much easier. But you have to kind of learn the hard way first to kind of respect the master theorem and to better understand recurrent relations themselves. So that is what is in the site. Again, this stuff is the hardest part of the class, frankly. After this, it gets easy. So hopefully you guys are following up. If not, this video will go on YouTube so you can watch it again. You can also go online and find lots of resources on Big O and recurrence relations when we get to that. That's a starting point. I did link, and I'll link again, the Big O Wikipedia. You can start reading there. You can read that. There's tons of resources. The book that I recommend on the syllabus does, which is free, and the link is available on the syllabus, does, I believe, have a section on this stuff. So you can read that as well. And if not, you can always ask questions. Send me email, post on Discord, and so on, and talk to the TA. We'll get to you. So cool. That is the class. So I will be posting that again, the assignment over the weekend, so you guys can get started on that if you'd like. Again, it's an easy assignment, but it's going to start to get you to think about your code in the sort of asymptotic complexity. And I welcome you to look at your old assignments and try to analyze this asymptotic complexity. That could be a cool thing to do. Maybe we should do that for the first assignment. You know, you should analyze the asymptotic complexity of the first assignment in terms of specific things, like how long it takes to generate the random name. How long does it take to generate the random name? Probably O of n time, because all you got to do is you got to loop through it once and pick a name, right? Or does it even take that? Or is it a constant time? It might actually be constant time, because you don't even loop through the names. You just generate a random number and then go to that index, right? So technically, I think it's constant time. So see, these are the kind of things you got to start thinking about when you're doing your programs and analyze it in that sense, you know? So you would also get more memes now. There's memes out there that talk about asymptotic complexity. Like, there's a skeleton lying in the bench saying, waiting for my program to run with asymptotic complexity n times n, or something like that, or n to the power of n. And so it's funny because n to the power of n is a really bad time complexity, right? But see, you're high level now. You understand that meme versus like before, right? So yes, a whole new world of memes just opened up to you. So with that, I will call it a day. And since I won't see you until next week, I suppose, I wish you guys not only a good weekend, but also a happy Labor Day and long weekend. Take the time to relax. The hard times are coming ahead, so might as, in terms of class assignments. So definitely enjoy this rest and make sure you're well rested so that when things ramped up, you're ready to go. All right? So with that, take care, and I'll see you soon, everybody.